Let's consider that we have a family of curves given by y squared equals kx cubed. And they're a family of curves because for any particular value of k, we'd have a slightly differently shaped curve. We are going to find orthogonal trajectories to this family of curves. It would be useful to remind ourselves that orthogonal means that the curves meet at a right angle, and more accurately, their tangent lines are perpendicular at the points where the curves meet. Perpendicular means that we're looking for slopes, or negative reciprocals. So what we're going to do is we're going to start by finding an expression that will give us the slope for y squared equals kx cubed. Differentiating both sides with respect to x gives us 2y dy dx, that is not a y, is equal to 3kx squared. Using this, we've got that dy dx is then equal to 3kx squared over 2y. Now, we have a bit of an issue here because k can represent any real number. That's what gave us the fact that we had a family of curves. So here we'd have a variable x, a variable y, and then this variable value k, and that's not all right. So since k can represent any real number, we need to replace it. Now, going back to our original equation, since y squared equals kx cubed, it follows that k is equal to y squared over x cubed, and we can replace that in the derivative. And when we do, we end up with dy dx is equal to, I'm going to separate some things out here, 3/2 y squared over x cubed, that was our k, times x squared over y. Simplifying, we can divide out one factor of y and two factors of x, and so we get that dy dx in terms only of x and y is 3y over 2x. So for any point xy, we now have a slope that's for the tangent line to one of the original curves in the family that was given to us. We want to consider an orthogonal trajectory, so we want tangent lines that are perpendicular. And for that, we're going to use the negative reciprocal. The family of orthogonal curves has a slope dy dx that is equal to negative 2x over 3y. The negative reciprocal will give us a perpendicular slope. Now, folks, what we're actually after is what is the family of curves? And here we have, guess what? A separable differential equation. So we get that 3y dy is equal to negative 2x dx. And now we can integrate both sides like we've been doing this entire section. So 3/2 y squared is going to be equal to negative x squared plus c. This isn't really going to clean up nicely if we try to solve for y, but what we can do is make this look like something we're kind of familiar with. So I'm going to multiply both sides by 2 to clear the fraction. So we get 3y squared is equal to negative 2x squared plus c. This new c is actually twice the old c, so I'm going to call the first one c1. And if we get x and y on the same side, then we get 2x squared plus 3y squared is equal to c. And that's a pretty nice looking equation. We'll leave it there. Now, let's see what we just did. I have here some graphs. Our given family of curves, remember, was y squared equals kx cubed. Our orthogonal trajectories are given by 2x squared plus 3y squared equals c. Those are a bunch of ellipses. And here's what we have. So I graphed the original family of curves for various values of k. So y squared equals x cubed, y squared equals 4x cubed, y squared equals negative x cubed, and y squared equals negative 8x cubed, just to give us an idea of what those look like. And they're these ones that look kind of like a branch of k, the letter k. And then, of course, we have the one that's over here in the second and third quadrants. Then the 2x squared plus 3y squared equals c, I graphed for c equals 1, 4, 8, and 15. And those are our concentric family of ellipses. And the point here, folks, is that whenever these original curves intersects one of these ellipses, at every single place where that occurs, the tangent lines of the two curves are perpendicular to each other. So that's what we've just found with orthogonal families of curves, orthogonal trajectories. The orthogonal trajectories will meet any one of the original curves at a right angle every single time it meets one. Let's do another one of those. Find orthogonal trajectories to the family of curves given by y equals 1 over x plus k. I'd like you to pause the video and come back when you're done. Well, I hope that went well for you. Differentiating y equals 1 over x plus k uses the power rule, so dy dx is equal to negative 1 over the quantity of x plus k squared. Since k can represent any number, we need to replace it, and we're going to do so by, again, starting with the original equation here, y equals 1 over x plus k. Clearing the fraction gives us xy plus ky equals 1. Solving for ky, we subtract xy from both sides and then divide by y. We get k is equal to 1 over y minus x. Since our denominator had the square of x plus k, we now have the square of x plus 1 over y minus x. The x's subtract out. So dy dx becomes 1 over y squared. That's negative. And so the result is negative y squared. For the family of orthogonal trajectories, the negative reciprocal of that slope would give us that their dy dx is equal to 1 over y squared. That's a separable differential equation, which will lead us to y squared dy is equal to dx. We went ahead and integrated both sides. On the left-hand side, 1/3 y cubed. On the right-hand side, it equals x plus c1, because once I clear the 1/3 fraction, that constant changes. And so I have a final result here of y equals the cube root of 3x plus c. And as before, for a visual of what we have done, we started out with curves that look like y equals 1 over x plus 2, y equals 1 over x plus 5, y equals 1 over x minus 3. And those are the hyperbolas that we see here. And then what we just found was y equals 3x plus k to the 1/3. And so I let k equal 4, negative 4, 8, and negative 10. And that gives us these they look like cube roots on their sides, because they are. And we'll note that anytime one of the hyperbolas intersects one of these cubics, they do so in such a way that their tangent lines are perpendicular to one another.